This lesson is all about intermolecular forces, which sounds fancy, but it's really not if you just break apart the words. The prefix inter means between two different things. So for example, if you play intramural sports in college, you're going to play different colleges. So NC State intramurals would play UNC intramurals. The prefix intra means within. So if you played intramural soccer, you would stay within your school, and maybe one dorm would play a different dorm, or one sorority would play a different sorority. So intra is within, but inter is between. So intermolecular means between two different molecules, and forces just means there's a force of attraction. So up until now we've talked about the bonds that hold something together. Now we're going to talk about once you have those molecules that are held together by bonds, those molecules can have forces of attraction. So the key word here is the capital letter between. These are attractions between two different molecules. These are not bonds, and so they're a lot weaker. It's not holding the molecule together, it's just an attraction between two different molecules. And there's three types of intermolecular forces that we're going to do: dipole, dispersion, and hydrogen bonding. Now keep in mind this says bond, but it's not actually a bond. I don't know why they call it that, but they just do. So keep in mind that it's really just a force of attraction. It's not a bond that holds it together. The first one is called a dipole interaction, and this happens between two polar molecules. So it's exactly like what it sounds. Di means two and pole means polar. So a dipole is between two different polar molecules. And this one kind of makes sense because you should be familiar with the word polar. It means that the electrons are not being shared evenly. So you have one side of the molecule that's slightly negative and one side of the molecule that's slightly positive. So you're dealing with kind of opposite charges, so it's similar to an ionic bond, but it's a lot weaker because it's not a complete positive and negative. It's just a partial positive and negative. So here's an example. If you look at HCl, chlorine is very electronegative. So all these electrons here in the middle are being sucked towards that chlorine, and so it's going to make it slightly negative. Now chlorine is still sharing with the hydrogen a little bit, so the hydrogen still gets them somewhat, which is why it's a covalent bond and not an ionic bond, but it's not an even sharing. It's not 50-50. So if you look at this HCl molecule on the left, compare it to the HCl molecule on the right, when these two molecules get close to each other in the beaker, they're going to align themselves so that the chlorine of one molecule is near the hydrogen of a different molecule, because this partial negative is slightly attracted to the partial positive in the hydrogen. You would never have two molecules where the chlorine and chlorine are near each other because they're both negative, so they're going to repel. So this, where the red dotted line, that is the attraction that we call a dipole force. It's that force of attraction between two polar molecules. The next one is a little bit different. It's called dispersion forces, and this one is between two nonpolar molecules. And you may think that if they're both nonpolar, there's nothing that will stick them together because there are no charges. I'll show you why though. So the electrons can move around the atom. So if we have two molecules, this is F2 and this is F2. So it's two fluorines bonded together and two fluorines bonded together. I just drew it as a circle, but it's a whole molecule. So each of these molecules has these electrons that are just swimming around the whole time. They're constantly moving around the whole time. And the way I picture it in my head to make it more concrete is I picture a classroom full of kindergartners, and if you said run around the classroom, so you had 35-year-olds running around the classroom, just like this. For the most part, they're going to be spread out throughout the classroom. But just by chance, for some reason, all of the kindergartners could end up by the door. They just happen to all be in one spot for a split second. And that's what happens to electrons. So since they're always moving around, they could just happen to end up on one side of the molecule, and that makes this side negative and this side slightly positive. So it's not a complete negative, just a slight negative. Then what happens is the molecule next to this one, their electrons are going to move too, because these electrons are very repelled by the slight negative here. So these electrons, since they don't like that slight negative charge with this lopsided electrons, they're going to move to the other side of their molecule. So all the electrons on the second molecule are also going to move away from this negative charge here. And now you have two molecules, both of which have a slight positive and negative charge because the electrons just happen to get lopsided. So now they're going to be slightly attracted to each other here. But this only happens for a split second. So as soon as those electrons start moving around the molecule again and they spread back out, the attraction is gone. And that's why this is the weakest of all the molecular interactions. It only happens for a split second. So again, they start off spread out because it's nonpolar. Just by chance, since all the electrons are moving, they could end up on one side of the molecule. If that happens, it gets a slight negative on that side, which pushes all the electrons in the molecule next to it to the other side as well. Then you have two molecules with slight charges that are going to be slightly attracted. But again, it only happens for a split second. The last type is a special kind called a hydrogen bond, but again, it's not actually a bond, it's just a force between two molecules. This is when you have hydrogen of one molecule that's attracted to either nitrogen, oxygen, or fluorine of a different molecule. Notice the word different is in capital letters. So it's important that you have two different molecules. For example, if we take water, the oxygen of water has a slight negative charge because water's polar. The hydrogen part has a slight positive charge. So the oxygen of one water is slightly attracted to the hydrogen of a different water molecule. So this red dotted line is the hydrogen attraction, the hydrogen bond. A lot of people will try to tell me that this is the hydrogen bond between this O and this H, but keep in mind that's a covalent bond. It's within the molecule, so it is not an intermolecular force. The intermolecular force is between these two, this oxygen and this hydrogen. And this is the strongest of the three that we talked about today, and it's also the reason that water has all of its special properties. So for example, capillary action and surface tension and the fact that ice floats instead of sinks, all of those can be explained by hydrogen bonding. So when you look at a sample of oxygen, and I don't just mean one oxygen, because if you have a sample of oxygen, you have a ton of atoms and ton of molecules. So if we have a whole bunch of oxygen near each other, I want to know what kind of intermolecular forces would those oxygens have for each other. So if you sketch out oxygen, it's just a double bond between two oxygens, so it's nonpolar. So if you have two oxygen molecules next to each other, since they're both nonpolar, that would be a dispersion force of attraction. Anytime you have nonpolar molecules, it will always be dispersion. For HF, the fluorine is very electronegative, so it's going to suck the electrons towards it and make it slightly negative on the fluorine side. So if you have a whole beaker of HF molecules, the fluorine of one molecule will be attracted to the hydrogen of a different molecule. And that's because they're both polar, which is dipole. But since you have hydrogen and fluorine, the hydrogen of this molecule could be attracted to a fluorine of a different one, which is also hydrogen bonding. So this molecule actually would have dipole and hydrogen bonding if you had it within the beaker. For the next one, if you sketch out H2S, the sulfur has two sets of electrons on the middle atom, so there's 4 total dots on it, which makes it polar. So this one's definitely going to have dipole interaction. It cannot have hydrogen bonding because there is no nitrogen, oxygen, or fluorine, so it's just going to be dipole. For the next one, carbon's in the middle and it's single bonded to 4 hydrogens. So there are no extra electrons on the central atom and it's the same element all the way around the outside. Both of those conditions makes it nonpolar, which means it has dispersion forces. For the next one, it's very similar, but instead of one of those hydrogens, you have a chlorine, which makes it lopsided and that turns it into polar, so it definitely has dipole. It doesn't have hydrogen bonding because there's no nitrogen, oxygen, or fluorine for this hydrogen to stick to. Carbon dioxide has carbon in the middle, and there's 2 double bonds, one to each oxygen. So this one ends up being nonpolar, which makes it dispersion. And for the last one, you have hydrogen single bonded to carbon, and then a triple bond to nitrogen. So the fact that you have different elements on the outside of the molecule makes it polar, so it's definitely dipole. But you also have H and N. So if you have an H of one molecule and the nitrogen of a different molecule, it means you could also have hydrogen bonding. So what you want to look at is, first of all, is it polar or nonpolar? Nonpolar would be dispersion, polar is dipole. If it's polar, check to see if you could have hydrogen bonding. This chart right here is going to be really helpful to you. So I arranged all of the different types of bonds and intermolecular forces in terms of their strength. So first of all, notice that bonds are much stronger than intermolecular forces. Of the bonds, ionic is the strongest because it has the biggest difference in electronegativity. Polar is second strongest and nonpolar is the weakest. but all three of those are still stronger than the three intermolecular forces. And of the IMFs, hydrogen bonding is that special one that's really strong, and then dipole, and dispersion is the one where the kindergartners run around and get lopsided, so since it just happens for a split second, it's going to be the weakest. And the reason you need to know this scale from strongest to weakest is in case I ask you about melting points or boiling points. So the stronger the attractions, the harder it is to break apart a solid or a liquid. So if you have an ice cube and you're trying to melt it, if it has really strong attractions, it's going to take more heat to melt it. So you might want to put it next to strongest up here. These things have the highest melting points and boiling points. The weakest has the lowest melting points and boiling points. So if I give you a list of compounds and say which one has the highest melting point, obviously I'm not going to ask you to memorize melting points for all the billions of compounds there are. So what you need to do is decide what kind of bonds and intermolecular forces does it have. And the stronger it is, the higher the melting point and boiling point. And the last thing for today are polyatomic ions, which is kind of an introduction to something we're going to do in the next chapter. Again, it sounds fancy, but it's really not if you just break it apart. Poly means many, atomic means atoms, and ion we've already been talking about for months now. It means it has a charge on it. So a polyatomic ion is a group of atoms with an overall charge. For example, sulfate is SO4 with a -2 charge, so it's 5 total atoms, 1 sulfur and 4 oxygens. All 5 atoms together has an overall charge of -2. So that -2 doesn't just go to the oxygen, it goes to all 5 of them. So if I ask you, for example, on a test, which of the following is a polyatomic ion, you first of all make sure it has more than one atom. So if I just had Na+, Na is just one atom, so that's not going to be polyatomic. Also make sure it has a charge. If I had something like CO3, that is not a polyatomic ion because there's no charge on it. So 2 things, make sure it has lots of atoms and it has an overall charge. And that's the last thing for this chapter, so that should be all of the information you need for the bonding test.